Okay, so this is the recording of the lecture that I'm posting later. So, in the last class, what we had seen was we had started with the problem of manipulator position control for the manipulator, and we had gone through the motions, and we had taken we had seen a few very simple the responses or the responses of a very few very simple systems like the first order and second order system to various signals, more particularly the step signals. We have gone through the concept of a transfer function and briefly introduced the state space, linearization, and certain simplification that may be required while dealing with the manipulator control. Okay, so in this lecture we'll go a little further into the analysis of the problem. Okay, what we'll be seeing is that in case of robotic manipulator, what we have is that you have a goal position and you have some position at the initial time. So let us say you have q of 0 and you have q of some desired that is there. So what can happen, and now you want to go from not this q of 0 even, what you have is the case where you have some xyz position or even theta phi psi. Okay, and you want to go to a desired position, desired final position. It may happen that you this requirement may be that you have to follow a trajectory that is time dependent, or it may also happen that you just have to go from pass through different points in this entire exercise. Okay, say there is no time dependency, but you have some waypoints which have to be followed. Okay, so finding out this path or this trajectory is path planning. However, these paths are expressed in the workspace coordinates, that is xyz, not in the joint coordinates. So you have inverse dynamics that will express this will translate this coordinates, this workspace coordinates back into joint coordinates and give us the desired joint variables trajectories. So what you start here are some x desired, y desired, and you have x desired of t, y desired of t, that through inverse dynamics you get theta 1 desired for t and theta 2 desired for t. Okay, however, you would need an actuator to give to power the joint so that this particular movement of your joint variables can happen. So the actuator is usually a motor, and the actuating signal is the voltage to that motor. So if you give a voltage to a motor, you get a motor torque, and that motor torque is going to move the joint to its desired position. Okay, and as I said earlier, the objective can be to reach one or more specific sequence of points with no time constraint. Okay, or it may need to follow a specified time trajectory where there is a time constraint. Okay, the first thing is the first sort of motion is called as set point. So there is a particular set point that has to be reached. It is also, this problem is also sometimes called as regulation problem, which means that your desired trajectory is just a constant. Okay, or it can be a tracking problem where your desired trajectory is going to be a time varying signal. So you have theta d of t, or theta d dot is not necessarily 0. In the first case, theta d dot was 0. And that's the way that is these two objectives can be differentiated. So we will first initially only consider cases or problems where theta d dot is 0, that is the set point tracking. Okay, and for now we will also see only the set point tracking where there is a single step. I have one point that is to be reached, and not a sequence of points are not being considered. So I have to go from some point A to point B. I'm initially at point A, I want to go to point B, and that's it. Okay. Okay, so what we have here, that first of all we want to simplify the model. Okay, and for that purpose we will be using the concept of independent joint control, that is each joint is considered separately. Okay, and for that purpose we have to first ignore the fact that the joints, the dynamics of joints influence one another. Okay, so each axis or each joint is to be controlled as a single input single output system, the input here being the actuator signal and the output being the joint angle. Okay, and all the couplings that are there in the joint variables are going to be treated as disturbances. So this disturbance di of q of t, q comma t, is the disturbance variable, where this dA of signal is all the cross coupling terms that are there, and even the gravity term is being taken into account. Some other, the gravity term of other variables, theta qi, where I is qj, where j is not equal to I, those contributions to this gravity are taken as a part of the disturbance variable. Okay. Okay, and this brings that to the objective. So now what you have is the plant is almost linear. Okay, the linear plant, this is your actuator, and this is the compensator that you have to design. Okay, so you have a reference trajectory theta d, which is a constant in this case, or it may be this entire picture works well even if the reference trajectory was not a constant, but let us consider the constant. So, and the output is this theta that you have, and the input is this theta z. This sensor is what measures theta and tries to convert it to a signal that can be compared with theta d. So this may be an encoder, optical encoder, that measures theta directly, or it may be a tachometer that measures the speed of theta, that is omega. Okay. Okay, so here is the type of control, the aim that we want to achieve. So here what you have is a setup of a inverted pendulum. So what this pendulum is doing is that it is in an inverted position, so it is already at an equilibrium point. Okay, where so if there are no disturbances, the pendulum would remain in this equilibrium position. However, what can happen is that if there is a small perturbation, the result is that the pendulum will fall down. Okay, the control objective here is that, assuming that the pendulum is very close to this inverted position, we are applying a control, we are designing a control, designing an actuator signal, where the actuator is actually the motor that regulates the motion of this cart in the horizontal direction. Okay, and the aim of the control is that the pendulum position remains in the vertical position, okay, despite any disturbances that are being given to it, like the tapping that is seen in this video. Okay, so the limitation for that is that the aim is to keep it in this vertical position, say, despite disturbance. Okay, however, the limitation is that only small deviation, only small delta theta can be accounted for, because if there is a larger deviation, there is a significant change in the model, so that it is the model may not be so simple that a linear time invariant model can actually describe it. Okay, so for large deviations, you don't worry, you can't authenticate the control that we are discussing, we would be discussing in the subsequent lectures. But for small deviations, it is okay, you can go ahead. Okay, okay, and so what we have been seeing is that there should be a mechanism for the application of the torque to the manipulator joint, and the mechanism by which this torque is produced is the actuator. Okay, and the actuator that we'll be choosing, that we'll be exploring, is a motor, which of course would convert the voltage to a torque. And there are different types of motors. Okay, you can have a motor in which so basically a motor will have a stator and a rotor. Okay, you can have a motor in which let us say the stator is going to be a permanent magnet. Okay, and the rotor is supplied by some voltage V. Okay, or you can have both the stator and the rotor being supplied by some voltage. Okay, so you can have separately excited or serially excited motors, DC motors. You can have the supply being AC, you can have DC AC motors also. Okay, but for the purpose of this lecture, we are only considering the simplest case of a permanent magnet DC motor, where the stator is a permanent magnet and the rotor is supplied by a voltage V. Okay, okay, now if you go to the basic principles of this motor, you may have seen in your first course on electrical engineering that when a current carrying conductor is placed in a magnetic field, it will experience a force, and the force is given as this F is I cross phi. Okay, and we have seen in the permanent magnet DC motor, PMDC motor, the motor would have a stationary stator and a moving rotor. Okay, and we also see that in this case of a PMDC motor, your phi has a constant magnitude. Okay, and if since it's a permanent magnet, if you are able to supply a radial magnetic field, okay, that is, this magnetic field is always perpendicular to the direction in which the rotor is the rotor coils are arranged. Okay, let me draw it in a different manner. Okay, so if you have your permanent magnet like this, okay, this is the north direction, this is the south pole, and you have the current flowing in the rotor. So this is the rotor, this is the stator, you have current flowing through the rotor. Then if the current is always radial at all times, okay, so this will produce a a force that will move the state rotor. Okay, now if the magnetic field is, let us say, is in the x direction, and the motion of the or not motion, the current is flowing in the y direction, phi and I, then the force will be in the z direction. That is, now this will mean that the force in this case, in this scenario particularly, it is in the z direction, so it is coming out of the page right now. Okay, it's perpendicular to this, and you would see that due to the direction of the current, okay, due to the direction of the current and its orientation with respect to the magnetic field, these torques actually, these forces will actually produce a torque that will cause rotation of the rotor. Okay, so it's going inward on one direction, it's going outward on the other direction, so effectively there is a torque produced. Okay, and now this torque can be related to the flux and the current by k1 phi a, because, and that is because it becomes phi into ia, because these two, because of the magnetic field being radial, the angle between phi and I is going to be 90 degrees. So I cross phi is I phi times sine 90, so it is going to be 1. However, there is also one more phenomena that is present in this setup, that is, whenever a conductor is moving in a magnetic field, there is a back EMF that is generated, and the magnitude of this back EMF is proportional to the velocity of motion of that current carrying conductor. Here the rotor is the current carrying conductor, so we are talking about the velocity of motion of the rotor, or the speed of rotation of the rotor. Okay, and so basically you have the current carrying conductor is moving in the magnetic field, and the magnetic is generated whose magnitude is proportional to omega m, in fact omega m times phi. Okay, but in this case, in the case of a permanent magnet motor, this phi is going to be constant, so you can say it is proportional only to the velocity of motion, which is the only variable that is available, which is present now in this case. Okay, so this is the a diagram of a PMDC motor. So you have the rotor being connected through this brushes, okay, to a DC supply, and these are the radial magnetic fields, radial magnets. Okay, so a radial magnetic field is generated here, which is always perpendicular to the direction of current in the rotor. Okay, and so what we have here is that a setup in which you have a voltage being supplied, and since the rotor coils would have some inductance and some resistance, there is a current, there is a armature current IA that is flowing through the entire circuit, and there is a voltage, there is a back EMF at the armature, and this back EMF is due to the flow of the current itself, due to the motion of the rotor. Okay, and anyway, finally there is a motion of the rotor, that there is a theta m angle motion of the rotor, and the rotor in effect delivers a torque tau m, and can tolerate a torque tau L that is coming from the output side. A low torque tau L is being affecting the motor, and all of them are going to affect the entire system. Okay, so let's see what is happening here. So what we have here is that if you go again to the previous slide, you'd see that V is equal to L di by dt plus R plus VB. Okay, that's the equation here. The torque, the mechanicals, on the mechanical side, the current to torque have a relationship that tau m is K1 phi Ia, which we can, because of the phi being constant, we can sort of write it as Km times Ia where km is the motor constant, you can say. And for the back EMF, Vb is proportional to the speed of rotation of the rotor. So you can have a back EMF constant Kb relating the back EMF and the speed of rotation. Okay, now at rated voltage, you what you have here is that Ia settles to some value, okay, settles to some Ia0 very quickly. So dia by dt goes to 0 quickly. Okay, so after a very very small time, this first equation gets translated to R times Ia is V minus Vb. Okay, let's say that you have given a rated torque Vr, so this becomes Vr minus Vb. Now on top of that, if you make omega m equal to 0, then you have made Vb also being equal to 0. Okay, now what does that mean? That would mean that this factor is not there. So R times Ia has become Vr. Okay, and at this point of time, it is going to give some torque. Okay, it is going to give some torque, and this torque is, let us say this torque is this tau 0. So you can relate tau 0 and Vr and the motor constant Km with the relationship Km is R tau 0 by Vr, or tau 0, because motor constant is depending upon inside the motor, so tau 0 is Km Vr by capital R. So as the voltage increases, the torque will increase, the tau value will increase. However, now if you see that if you again analyze this, when Vb is not 0, you would end up with the relationship that R times Ia. Okay, let's go to the next slide and do that. Okay, so what you have here is R times Ia.
But first you have to unlock your device.
What you have here is R times Ia is Vb, so V minus Vb. Okay, now R times Ia is proportional to tau m, so tau or something k times tau is V minus some alpha times omega. Okay, let's not go into this thing. So as omega increases, what is happening is that for the same voltage, the amount of torque that is available will start to decrease. Okay, and this decrease is also linearly proportional to the speed of rotation. So the speed to torque characteristics torque speed characteristics can be expressed in this manner, where you have lines of negative slope. Okay, and as the voltage increases, as the supply voltage increases, these lines will go up. As the rotor speed increases, the available torque will go down. That's the takeaway point that we have here. Okay, next one thing that we have to see is that generally the motors that we have are run at quite high speeds, at hundreds of rpm. However, they don't have the capability to generate high torque, because when they are running, the torque is decreasing because of the back EMF. When the motor runs at higher speed, the torque will decrease. When the motor runs at low speed, the torque is larger. Okay, however, on the other hand, you have the manipulator that need not move at very high speeds, so they need to move at low speeds only. However, they need high torques because of the mass of the manipulator. I can move the manipulator at low speed, but I want higher torque to move the manipulator in the first place. So there is so you need a mechanism by which the power can be transmitted from a high speed low torque actuator to a low speed high torque load. And the ideal piece that will fit here is to use a gate ring that can be used for the conversion of this power. Okay. And what you need is a gear train that will convert from a high speed to low speed. So you need a gear train which has a high gear ratio and looks like this. Okay, so this is your actuator, this is your gear train, this is your load side. Okay, and the motor angle and the angle of the load are related by this relationship that theta m is r times theta s. So if you have, say, theta m, or rather omega m is 200 radians per second, okay, and you have a gear train r is 200, then your load, let us say omega l, is only rotating at 1 radians per second. Okay, so you have effectively made something that will convert a low speed high torque you have converted a high speed low torque actuator to be able to supply power to a high torque low speed load. Okay, now let us see the dynamical equation that will govern this side. Okay, so there is a torque in this direction. Okay, and there is a low torque, but however um, due to the gear train, so you have tau m in this direction and tau l by r in this direction, and the resultant is what is actually we are seeing as the rotation of the motor. So at the motor side, you have the total inertia of the motor is ja plus jg, which is, let us say that the motor inertia is jm. So jm d square theta m by dt square plus this damping bm, so b dm d theta m by dt will be the effective torque, that is tau m minus tau l by r. But tau m is related to the current, the motor current ia. Okay, so that is km times ia. Okay, and if you use the Laplace transform for this, you end up with a second order differential equation in your variable theta. Okay, and that is related on the right on the left hand side, or on the right hand side you have the motor current ia and the load torque tau l. Okay, and in addition to this, you also have the electrical equation which relates the voltage v to the motor current ia, the supply voltage v to the motor current ia, and the motor angle theta m. Okay, that is given by this equation, L di by dt plus ria. Okay, and that will give you this Laplace transform, also this Laplace transform relationship. Okay, now we have already seen in the last class that all these Laplace transforms can be converted to transfer functions if I know what I am interested in. What I am interested in here is the relationship between my motor angle, the load torque. I am not so interested in IA because that is not something that I am directly controlling. What I want is the relationship between theta and v and theta and tau l. So these are the transfer functions that I want to find out, and if I write it, if I represent all the entire drive dynamics, what I end up with is a block diagram like this. And if you solve this block diagram, what you end up with are two transfer functions. one representing the relationship between the voltage and the motor angle, the other being representing the relationship between the towel and the motor angle, okay, given by this third order transfer function, because you see that there are three s's appearing in the denominator, so the order is 3, and it is slightly difficult to analyze third order system as compared to first order system. So you have to first see whether this entire thing can be actually simplified. Okay, can some simplification be done in this case? Okay, and the answer is yes, it can be done, because what we have here is a combination of an electrical system and a mechanical system, and the electrical system has a response time in milliseconds, and the mechanical system has response times in a few seconds. Okay, and what we are actually interested is the response of the system of your entire system in the or in the time frame of few seconds, and we are not so interested in the time frames of a few milliseconds, as long as we know that the system is not unstable. The modes which are fast are not unstable is what we want to be assured about. Now let's see both of those cases. So when you say ls, how do you analyze that whether the mode is stable or not? We see that if this the solution of ls plus r equal to 0, is that s on the left hand side or the on the right hand side of the imaginary axis? Okay, ls plus r is equal to 0 would give s is equal to minus r by l. Okay, so when you have minus r by l, which would mean that since r is greater than 0 and l is greater than 0, because inductance and resistance are both positive, you would end up with a situation where s is on the left hand side of the imaginary axis, and even there it's on the real axis on the left hand side of the imaginary axis, which in turn would mean that this is a stable system. So that is one criteria. Second point is that in general there is much less inductance as compared to the resistance. So what you end up with is a situation there where L by R is much less than 1, and L by R here, if you do this thing, so this you can represent it L by R s plus 1 is equal to 0. This is equal to the time constant of my system, okay, of this electrical system. So you have an electrical system whose time constant is very small, okay, which in turn would mean that if I see this system in the scale of in the time scale of a few seconds, you see a response that is almost instantaneous. So you can ignore this response, and you can say that my L by R, my L is approximately 0 when compared to R. Okay, so you can say you can approximate Ls by R to be approximately equal to just R alone. Okay, and now if you proceed further using this approximation, those two third order transfer functions will be approximated by equivalent second order transfer functions. Okay, so you have this second order transfer function here, and in the second order transfer function, if I write it in a differential equation format, you get this second order differential equation that relates the input voltage, the load torque, and the motor angle. Okay, and we also seen that we have a gear train, and we have also seen that in the gear train example we have taken, let's again go back and see the gear train, this thing here, we have also seen that the motor angle and the angle of the load, that is the joint variable, are related by theta m is r times theta s, and the load torque is just translated here, okay, by, so the load torque here is the same as the load torque that I have from the joint. Okay, so if I come here, you have r times q is theta, and tau l at a joint is the same as the load torque that is experienced by the mm, motor on the motor side also. Okay, so that is what we wanted to cover in this lecture. Okay. We will go to the concepts of PID control and further in the next lecture.